Well, Coco, I've been thinking about making a YouTube video about improving the performance, safety, and reliability of these Lichtenberg so-called fractal wood burning systems. What do you think, Coco? Should we make a video about that? I don't know. Anyway, we just came down here to our local power plant where we... Okay, testing 1, 2, 3. Let's see if this is going to work. So this is a schematic. This is a schematic which is representative. It's one way to model a block of wood that you're going to Lichtenberg. Right now, this isn't a typical schematic. I took some liberties and added some things you wouldn't see in a professional drawing. But let's just go over the different parts of it here. Now, let's get the easiest stuff out of the way first. Our primary side of our transformer here, we've got our box, our electrical distribution panel, and through the wires in the house to your outlet, you've got neutral, earth, and hot connection. It's usually neutral is white, hot is black, earth is bare copper in the United States. Slightly different in Europe with this bonding connection here, and the colors are different. It's blue and brown, and they're both hot. In any case, in the US, we've got, I'm not an electrician, I'm an electrical engineer. So some of this is not going to be actually that relevant, because this is far more of an engineering problem than it is an electrician's problem. So consider this to be the outlet your Lichtenberg device is plugged into. Right here, I've got it labeled J2. J1 is the plug that's going into it. So that plug is going to make these three connections. Low will be going to low, your high side, your hot side will be going to hot, and the ground will go to ground, of course, earth ground. That is very interesting though, because it connects chassis ground to earth ground, which is also connected down here. I don't have it labeled, but this green bar is just to help us visualize some of these current flows. This green bar is supposed to represent ground. It's green because green's a color of a plant or a tree or a leaf or something conductive. Now, keep moving through this. So in this case, we have got ourselves a fuse in the circuit, a main power switch, and here representing a foot switch. So when these two switches are closed, we've got a circuit closed here, energizing the primary of the transformer. Now we're going to get up this table here in just a minute. The secondary of the transformer, we're going to talk about the biggest problem and probably the biggest potential killer in the way these things are built. People leave this connection here on the secondary side connected to the transformer's chassis. Okay? Then they connect that to the chassis ground of their box. Their metal box, their board, or their plastic box, whatever. That chassis ground, or they connect it just directly over here to the ground input on their connector. That's bad. Talk about why in just a second. Let me get through the rest of this circuit. So, terminal A here, we've got 2,000 volts AC. Terminal B, we have negative 2,000 volts AC. Actually, the way to look at this is when it's AC, A is more positive than B, B is more positive than A for half the time. It's going back and forth, it's alternating. That has nothing to do with the analysis. This could be done the same almost exact analysis with DC. So let's just consider A to be a hot wire, B to be the current return, although it's equally as hot as we'll see. Grounding it here does bring this level down to ground, but it also provides, I'm getting ahead of myself here, but it also provides current return paths that we don't want. Now, out here to our block of wood, this is our load, and I've chosen to show it and model it electrically as a bunch of resistors, as a bunch of little wee tiny resistors. Now, of course, if you put an ohm meter here and measured the resistance of a block of wood, you would get a measurement. It might be very high without the electrolytic solution, but there would be a measurement if you had a sensitive enough meter and can measure high impedances. What happens here during the burning process has got a lot to do with the safety. So consider for a minute, we've got our leads here connected to a bunch of resistors like this. Current is going to find the easiest path. Wait, before we get to that, let's talk about why I put these gray lines on the outside of the black wire. The black wire here is the conductor, the copper conductor inside the wire, and the gray is representing an insulator, and the arrows represent our probes. Okay, so what happens here is current will try to find a path from this probe to this probe. It will pick whichever path pleases it based on which one is the lowest impedance. If it will share, the current will be shared among all of these actually in inverse proportion to their impedance. Impedance is for this the same as resistance. They're not exactly the same in the engineering world, but it doesn't matter for this. If I say impedance, you think resistance, right? Which is really the opposite, the inverse of conductance, which is saying that electrons that are up here at this high potential 2000 are going to seek the pathways of best conductance, which is least resistance. Same thing. Like water goes downhill, it finds the easiest path to get down the hill. Fewest obstructions, steepest pathway, whatever. Getting back to electrons though, when this, let's suppose it picks this pathway. These dashed lines, what they mean is, in the schematic, that in between these dashed lines we have more resistors like this. So each of these branches that current can flow through has got more than 6 resistors in it. It's got thousands of resistors. You could say that one resistor represents one cell, like a biological cell in the tree. Trees are made of cells, just like people are, and animals. So, obviously there's a lot of cells. They're not all arranged neatly like this in columns and rows, of course, but it turns out, if you do a certain kind of calculation and mathematics on the whole thing, you can represent them just like this, and it makes it easier to see what's going on. Now, we've decided that this one is going to have the most current, because it's got the least resistance. What happens is, all of these resistors along here get warm. The whole thing dissipates energy because each resistor gets warm. That is what causes the little burning on the wood. When you get enough power into small enough of a volume, that volume just disintegrates. It basically it burns up, it vaporizes. You can only put so much power in a certain volume, and if you don't take away the heat, the temperature is going to go very, very high to the point where it is beyond the combustion point of the wood. So now this whole branch is gone, because if you eliminate one of these resistors, let's say this one blew out, it's gone. So you don't have current in this branch anymore. So what happens? Maybe this will become the next favorable branch. Now let me take a second here and talk about the model just a second. Another engineer could make the argument, and it would be correct, that the model should also include wires that go across in this direction. Okay, from these little, see these little squares right here? Here, let's zoom in on there. Those little squares are the connections between resistors. And if you did hook a wire in your model across that way, it means that if this particular resistor blew out, you could still have a current path from here down through, and then across that wire, and then down through this path, and across that wire, and down through this path, and until it gets to the lead back here, to the B lead where the current can return. So you can have all kinds of crisscross crazy pathways in here, but it doesn't matter too much. What matters is we understand that when one of these little sections gets blown out, that means the current has to find another way. That's why when one part of the wood burns, it's gone. It's done. Done there. The current has done its job, blown out the wood, moving on, and just burning the pattern. And as it hunts, as the current coming out of terminal A hunts for its best way to get to terminal B, that's what creates these patterns. These are, you're seeing the paths of least resistance in real time, reforming and reforming right in front of your eyes. That's what's so fascinating about this. Okay, now, suppose one block of wood with all of its resistors is a nice dry type of wood. You spray on some, you have to spray on electrolyte solution because it's dry wood's actually a reasonable insulator. It's not a great conductor. Wet wood's different, and wet wood that is absorbed in electrolytic solution, especially like baking soda and water, which has got a lot of free ions in it, when that solution gets into the wood, penetrates a little bit, all of a sudden it does become a better conductor. And the point is, if you found a piece of wood that was green and the right conditions, it would look like a dead short, or something, a very low enough resistance. I shouldn't say a dead short. It's not going to be like a piece of copper wire, but it could have resistance in the order of 1,000 ohms or less. It's not going to be 1 ohm or a fraction of an ohm, but it could be normally when you hook this up. See, I'm leading into this table right here, okay? Because this, what I did here was calculate the maximum current that you're going to have flowing in these wires. And all this, I'm sorry to take a small break here. Everything we're talking about here is leading up to current paths which can exist when you have this bad connection right here. And current can find its way back through this guy to Earth, through his little insulating boots or his sneakers or whatever, to moist ground, and then complete the path this way. Let me get back to this and finish this thought before we get to that current path that actually electrocutes old Reddy Kilowatt here. That was this guy's name from back in the 50s or 60s or something. The power company had this guy, Reddy Kilowatt. And he says, "Remember, kids, electricity will kill you." And he's actually holding a little stiletto knife here. It's so politically incorrect today. Remember, kids. Also, weird people will kill you. But electricity is our problem here. So, we were talking about these different current paths burning out and making the fractal pattern. When this block of wood, there's nothing here to limit the current traveling through this wood. The only thing that limits that current is the resistance of the wood itself. So if between the two places where you connect these probes, you've got a very low impedance connection, or just the right piece of wood, it becomes it can get to a point where you're actually drawing maximum current. Now the resistance you can figure out here. All we have to do is how many times is 0.825 going to 2,000, and that's actually the critical resistance. Below that resistance, you're going to be drawing too much current for your input circuit. Power losses in the transfer, and efficiency losses. That means we're going to be pulling 15 amps on our input side. Now, if you don't have a fuse here, a circuit breaker of some sort, you can allow far more than the 0.825 amps to flow through the block of wood. Now, the problem with that is that is going to be, more power is going to result, and more heating of the transformer. And look at the secondary winding of this transformer. Look at the gauge of that wire. It's good for almost an amp, sure. It's not good for 5 amps. Okay, if you tried to pump 10,000 watts through this transformer, that wire is going to get hot, melt, possibly melt the bobbin, and it's difficult to predict the exact cascade of events that would, what would melt, what currents would flow where, while this thing was getting hot enough to start smoking. And you can believe me, nothing smells worse than a burning transformer or burning electronics, to electricians and engineers especially. But they smell bad enough to regular woodworkers as well. And your wife won't like it. You don't want to exceed this current in the secondary, and the way to do that is to limit the current that could flow into the primary. If you're on a 15 amp circuit breaker back in here, you've got that working for you, so you don't absolutely have to have this fuse in place, but it's certainly safer to have this fuse handy where you can get at it. I would actually recommend that this be a 5 or a 10 amp circuit breaker here, and just control your burning such that you're not pulling so much current through this, so you're not really getting this transformer near its heating limit. That's a whole other topic of discussion, and I apologize for getting off the track here a little bit. What we're talking about, though, is what happens if we have this ground connection. We may not be standing on perfectly great ground under our feet. We might have insulating boots, we might have on insulating gloves, and so forth. But as these guys are burning, these different parts of the wood are burning, this probe and this probe, you can see, gets really black. It digs into the wood, and the connection gets kind of bad. It's why people have to move their probes around and things like that. It basically loses connection. Now the danger here, let's suppose for a second we did not have this chassis ground, okay? That is the good condition. That's the better instrumentation layout for safety. And here's why. Because if this connection fails, or this connection fails, it means that you no longer have a path where, and I'm going to follow the mouse here, let's suppose this connection has failed, okay? That means there's a pathway through the block of wood, through your metal workbench. Let's just say it's metal workbench, or it's a wooden workbench even, I don't care. So the current now can come through this setup into your workbench to ground, and follow me along here. It's traveling along ground. This ground symbol is the same potential as this ground symbol. I mean, your neutral line and your earth line are both at ground potential, very, very close to it. Now your return current path, remember, we're trying to get back to B here. You're an electron, you're coming out of A, you have 2,000 volts of potential pushing you or pulling you back to terminal B. That's where you want to get to. Your preferred pathway right through this lead has just been interrupted. That connection's no longer there. It's burned out. But you've still got this potential across these two. Electrons up here can feel that potential through any path to ground. Coming along here through ground, there's a pathway. Pathway comes back up here to earth ground. It comes over here, skips across to your chassis ground, which is also connected to your point B, your point B on the secondary, and that is your current loop. Let's go through that current loop one more time. Electrons at point A, remember, are trying to get through all these external paths to point B. Since this point, this connection, the normal return path is now gone, it means that A can go out to the block of wood, find any path it can to get to ground, because this connection here will now pull those electrons through ground, through this connection, and through this ground to your chassis ground, chassis ground to chassis ground, and fry you. So, it can be said that a plastic box is more safe if you haven't made this connection with a wire. Some of these Lichtenberg devices out there I've seen, people will take a piece of wire and connect this point to this point. They don't know that that piece of wire is entirely defeating the purpose of their plastic box. Okay? Now, let's talk about another safety technique. This red little bar here on your workbench represents a big rubber mat. Okay? Dry rubber mat without metal filings or tools laying on it or anything that can give you a path to this guy. So, what that does is the potential trying to get through this block of wood into ground now sees a resistance in this thing that's very, very, very high. So you do have a true leakage current here, microamps or microamps, very small leakage currents. If you put your hand on this block of wood here, though, it could very well travel through you to ground. Okay? So you've got your insulating gloves here, and your insulating shoes, and they're dry and in good condition and have been tested and inspected. If you reach over and touch this block of wood, or touch this probe to reposition it, things are energized. As long as these protective things theoretically are in good condition, you're not going to get a current path through you to ground and back around to this point where it wants, which is where the current wants to get to. So it's still never a good idea to work with these probes directly. Some guys have done it, or they do it. They use PVC pipes with nails in them and things like that. And this wire that we see running up through there is very often a heavy gauge wire, which is stupid because you're only running less than an amp. Period. You're running less than an amp. The insulation on those wires also, I'm going to talk about those for a second. Battery cables, stupid. It's less than an amp, and the insulation on the battery cables, on the jumper cables, is cheap plastic insulation. It cracks, it gets holes in it. It also, if you don't have handheld probes, which I hope you don't, and you've got a kind of probe where you clamp onto the wood, that heavy wire, it's under tension. It has weight. It's pulling on your connection and so forth. You don't want to have any tension on your connections. You want the force on the connections to be in the direction of the thing you're connecting to only, not a lateral force. It should be a vertical force into the wood. So that's another argument for reducing the diameter of these wires to something reasonable. Here, 1 amp, you could go down to smaller than 24 gauge wire. It's getting pretty fine. And if you look at the Alpha or Belden websites for selecting wires, they do have high voltage wire, which is fairly fine gauge. Oh, something else I probably should have put a calculation here. The industry standard and the mil spec, the military specification for dielectric insulation, dielectric withstanding voltage, used to be 2.5 times your working voltage. Okay, so 2.5 times 2,000 is 5,000. So the wire, the insulation you've got on this wire should be at least 5,000 volts. One other thing, and another advantage to using a smaller gauge wire, and I would recommend highly stranded, very flexible wire, is that you can use the insulation that you get with the wire, and then you also have the ability to put additional insulations on that. Additional layers of heat shrink tubing and things of that nature, especially out here where you're going to come up with some kind of a arrangement to do your clamping. I'm not going to recommend a specific clamping mechanical design. I'm not a mechanical engineer. But I have seen things on YouTube where there's exposure not just at the point of contact. There's additional bare metal on the clamps back here close to where you handle them. And that's not good. So that's a place where additional carefully selected insulating materials, you don't want to use bathtub caulking and things like that unless you do the research that shows that that exact caulking is suitable for electrical use and what conditions it's still good for. Okay, so I hope this made things a little bit clearer here, what the whole circuit situation looks like and some of these simple Lichtenberg devices out there, and why you want to get rid of this connection. You know, these mats, insulating shoes, a foot switch, plastic boxes, all good, but they're not the biggie. They're not the 800-pound gorilla in the room. It's leaving this connection in place that makes it possible for the current leaving this device into your wood to hunt for ways around this pad, for ways around your gloves, for ways, and here you are with blood in your body, and without these insulating materials, if that current can somehow penetrate your insulation, you're going to get fried, because that current is able to get to ground, come back through here, and satisfy the current, the voltage loop, and get back to this ground. Now, if you just cut the ground out, just cut that ground wire out, and concentrate on a really good insulation right back to the transformer. If you use any kind of connectors here, make sure that they are super mechanically well attached. They're not going to jiggle around, that there's not going to be any stress put on these wires that are going to disturb those connections. Make sure you've got a primary and secondary and possibly even tertiary ways to keep this wire that's conducting, right? This is the copper part here. Primary, secondary, and possibly even tertiary ways to keep this totally isolated from your case and everything until it makes its way the whole way out to your device. The feed through in your case, it's not shown in this diagram here, but this transformer's in a box or a case. You know, it's metal or it's plastic. Each have their advantages and disadvantages. But it's got to get through the wall of that. So that's a point where you can have trouble. You've got to take very careful care in selecting the appropriate connectors, and that all those connections are made nicely. Now, one last thought. There's a design out there. It's a nice looking machine. It's commercially available. I have asked the designer of this thing if he knows if this connection is intact inside his box. They have not gotten back to me. Here's the problem. If it is, and you pull this wire out of the box, out of the connector, and this wire is in the box, it still has the potential to sneak past. It's going to try, the current flowing through your wood box is going to try like hell to get back to terminal B here. And since this connection to chassis ground is in here, and that connects back to earth ground, if this guy's box is set up that way, it is designed to kill. All you have to do is pull out this cable here. It's probably the black cable on his device. I'm going to guess it's the black cable. It's got the earth ground. It's not the appropriate color code, but that's neither for here nor there. If you pull out that cable and you get yourself between your block of wood and earth ground here, you're going to die. Simple like that. So anyway, happy burning out there. Have fun with it. You know, if there's questions about this, you want clarifications and so forth, I'll be happy to make them. Just make a comment down below there. Be professional about it, and we can go from there. But don't waste the time with chatter, please.
Okay, Coco, let's talk about this a little bit, what we're going to do here. That behind us is a power plant, which seems a little bit appropriate because... Okay, Coco, don't be afraid. It's not a nuclear power plant behind us. Those are cooling towers. Every place with a turbine has them. And this place is natural gas powered. But that's got very little to do with this video. I run this channel, I'm playing with it, the Green Heart of Italy, because I'm a retired electrical engineer. I retired in central Italy. A little bit of noise comes in to me from the outside world. I can't help it. It's called my YouTube feed. And something has come up on that, because I love to build things, and it figured out that I would be interested in fractal wood burning, what they're calling fractal wood burning, Lichtenberg wood burning. And it is interesting. But so far, 30-some people have died from it. They've gotten themselves electrocuted because it's easy to do if you're not fully knowing everything that's going on. Enough about what's going on, let's put it that way. So I'm watching these things and commenting to people, and what I noticed was there's different types of people out there making these things. Some of them are sincerely trying to make the process safer and make these beautiful pieces of artwork, but they put these patterns in. It's like a lightning kind of patterns, or if you've ever seen a power line that's fallen on the ground, there are things that they're just beautiful patterns in the wood, interesting to look at, and they're having fun making them. And these guys are trying, some of them sincerely, to make them better and more safe. Some are cowboys, cavalier. They think it's not going to happen to them. And good luck. Good luck. See you in the afterlife, maybe. So I'm going to take my good time here and talk about leakage currents and help to fix one of the bigger safety problems that we're seeing on these systems. Okay, Coco, come here.